All right, we're going to take a look at quadratic functions, some of their basic forms, and the key features that are involved. All right, so features we've already talked about. We know that when we're solving quadratic functions, solving quadratic equations, we're looking for the roots, the x-intercepts or zeros of the function. We also know we want to be able to look for the vertex, and occasionally we might also be interested in the y-intercept, just like we would with any other function. I do have one additional feature that I've written here, which is called the axis of symmetry, which I kind of like that name, but we're going to talk about what that is, why it's associated with the vertex, and anything else that's kind of important about it in a second when you see the graph of a parabola. So we're going to start off with a really basic parabola. This is x squared, right? This is the parent function for all other quadratic functions. And all these features for this one are in the same place. So you have roots right here, the x-intercepts, the y-intercept, and the vertex are all in the same place. But the second you change anything about it, so you get some other function, suddenly the features are all different. So your vertex in this case is down here, your y-intercept is here, and your roots are there and there. So I did say I was going to mention this axis of symmetry feature as well. So here we have a function, it's a parabola, we can see where the vertex is. The axis of symmetry is a line that cuts the whole graph in half, and you can see that it's always going to run right through the vertex. All right, so it's really, it's closely associated. It's a line that's running along the x-coordinate of the vertex, so it cuts the whole thing in half, and it's called the axis of symmetry because you can see it's symmetrical. On either half of this graph, you're going to find points in the same place. So here, the y value is 1, and here on the other side, the y value is also going to be 1, and they're the same distance apart from the vertex, the same distance apart from the axis of symmetry. All right, now we're going to take a look at some of these different forms that quadratic functions can take and how they let us see these different features. So starting with factored form. So the factored form of a quadratic does just what you would expect. It looks like it's factored. It is factored, and as such, just like when you're solving quadratic equations by factoring, it would make sense that what it's giving us is a way to find one thing very quickly. So if I just modify one of these values, r1, one of these roots up here, and I make it 5, you can see that one of the roots is now 5. And again, if I drag one of these other, if I drag the other value, the r2, and say I make it 4, or negative 4 in this case, I now have a root at negative 4. All right, so if we use this form, we can very quickly find what the roots are going to be. Now, let me see if I can just quickly change over these roots to something that we can work with. And let's make that 4. That'll work well enough. All right. So we still want to be able to find the vertex from this form as well, and it's not that bad. So factored form, great for finding roots if they're whole numbers, and it's factorable, and if it's given that way. But it's not bad to find the vertex either, because if you look in relation to where these zeros are, you're going to see that the axis of symmetry and the vertex is just halfway in between. So you can at least immediately find the x-coordinate of your vertex by just averaging out your two roots, by finding the halfway point between your two roots. All right, so to summarize, factored form, great if you're looking for roots. Your roots are always just going to be right there. Your roots are at R1 and R2. And it's not bad for finding the vertex. All right, the x value of the vertex is R1 plus R2 divided by 2. It's the average of the two, halfway point. Standard form, we're going to come back to. So the vertex form of the function, pretty obvious what its strong suit's going to be, but let's go take a look. All right, so the vertex form, this is our function transformation form. Just like any other form, by the way, if you change a, you're just changing the how steep it is, how thin or how wide. And if you go into negative numbers, again, you're flipping it over the x-axis. Now you can see here if I'm changing h, the value right here in vertex form, the one that's next to x, I'm changing the x value of the vertex. And if I'm changing k, I'm changing the k value of the vertex. All right, so by changing those two values, we can affect what the vertex is. And if you just have a pre-written form of this equation, you should be able to immediately name the vertex by just identifying h and k as that point. Along with that, it's also going to be pretty straightforward to find the axis of symmetry, because it's just the x value of the vertex. All right, so in summary, this form's great for finding the vertex. All right, it's at hk. That's the coordinate of it. And it's actually not bad for finding the roots either, if you remember that the roots are just where, so if we have a function in vertex form like, I don't know, f of x equals 2 x minus 4 squared minus 8, well, finding x-intercepts are just finding the values where this equals 0, where y equals 0. And we're not going to step through this because you've solved this problem before. You know how to find the x-intercepts, the roots of a function in vertex form. All right, coming back quickly to standard form. Standard form is the standard form, but it doesn't really reveal very much. So if we go over, you can change a, and it's still going to just affect wideness, steepness. You can change b, and it's kind of not obvious what that even changes. It's not directly associated with the roots. It's related, but it's not clear. It's not like a number that matches right up to it. And c at least does identify the y-intercept, so it's great for that. So you can see here my value of c is 2.7. My y-intercept is 2.7. So that's nice. But the reason it's really there and the reason it's in standard form is not really that it's great for finding the y-intercept, which it is. It's that one of the main reasons we use quadratic functions is to model things in physics, and the values a and b, as well as c, both have really clear applications in that. So A would be acceleration that's happening on an object, B would be an initial velocity, C would be an initial location. So that's why we use that, but it's not great for actually finding features of a graph. We'd usually have to do something to modify it. And in fact, we need additional formulas usually just to do that. So you'd use, say, the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, to find roots, as we've done before. And then there's an additional formula, x, that comes from that same place, x equals negative b over 2a, that finds you the axis of symmetry, which will give you eventually the vertex, since it gives you the x value of the vertex. All right, so these are the main forms where you can get the features from them. We're going to continue to work with this for a while, but here's a nice